This is the 8th topic in the probability and stochastic processes course, in which we are going to discuss about discrete time Markov chains, or DTMCs. DTMC is one of stochastic processes. When we are talking about stochastic processes, more or less we are talking about a probabilistic behavior or something that is governed by probability. A stochastic process is a generalization of a random variable. So even in a random variable governs the behavior, the random occurrence of one particular event. Then a stochastic process is a sequence of random variables over time. So when time proceeds, then we make decisions on the value of each of these random variables. So we can denote them, this sequence, as x0, x1, x2, and so forth until xn, for example, where the index of the random variables basically denote the time. Now, the index of these random variables may be discrete or may be continuous. Discrete means that we can map them into the set of natural numbers, or continuous, in which case we can map them into the set of real numbers, leading to discrete time and continuous time stochastic process. So we can basically distinguish between discrete time and continuous time Markov processes, stochastic processes, namely stochastic process that proceeds in discrete time, namely in lockstep time, 1, 2, 3, and so forth, or in the continuous time. You can look at them like in real time. Now, each of these random variables that form the sequence of random variables that form the stochastic process takes value from a set of states, namely what we call state space S. This is what distinguishes this from random walk. This is also actually a sort of generalization of random walk. In random walk, we are dealing also with a sequence of random variables in which one random variable determines the direction that we are going to take in one step. Now, the random variable determines the state. So we have a lot more freedom, the state that we are going to occupy at one particular time step. Now also, the state space can also be discrete or continuous. So we have discrete state and continuous state. Now in this lecture, we are going to talk about discrete state only, and a discrete state space, namely those that can be mapped into natural number. In this case, we are going to map it from 1 until m, where m is the number of states, is called a chain. So a discrete state space is called a chain. Now the first chain that we are going to look into is the discrete time Markov chain. So from this, we can determine right away that the time proceeds in the discrete fashion. So discrete time, and this is a chain, namely also discrete state. But there's something more than we call that, namely what we call Markov chain. Why do we call it Markov chain? Well, this is a specific property of these stochastic processes, in which the chain must satisfy this Markov or memoryless property. Namely, look at this, the probability that at time step xn plus 1 is equal to j, given that at xn we are in state I, and xn minus 1 we are in state kn minus 1, and so forth, until at state x0 we are at state k0. This is equal to the probability that at state xn plus 1 is equal to j, where at state xn we are at I. What does it mean? It simply means that past behavior or past history is not relevant to our decision about the next state. So if we are currently, namely at xn, we are currently at one particular state, then the past history does not basically change. So what determines the future behavior is just the state in which we are residing right now. So the probability of these two things are the same, namely just determined by or the state that is occupied right now. So that means also that it does not depend on time. Yeah. So probability of transitioning from any state I to state J is determined only on the fact that we are residing at state I right now. And this must be constant. It cannot be variable. It cannot be in terms of a function. Yeah, it must be a constant, and it must be time invariant. It does not change with time. Therefore, we can denote this as just a particular constant. We can denote the probability that xn plus 1 is equal to j, given that xn is equal to I, as pij. So the probability from I to j, no matter whenever, it doesn't really matter when this happens, as long as we are at state I right now, then the probability to transition to state j will remain the same. Of course, there must be an additional condition that for all I, the sum of j is equal to 1 until m pij must be equal to 1. So that means that if the discrete time Markov chain is at a particular state I right now, then the sum of the probability of going out of this state must be equal to 1. Now, from these three facts, we can actually see right now, we can determine, we can specify a DTMC. How do we specify a discrete time Markov chain? So, a discrete time Markov chain is determined, is specified by three things. The first one is the state space S, which is a set that contains 1, 2, 3, and so forth until m, where m is the number of states. We always start with 1, so the first state will be state 1, state 2, and state 3, and so forth. And the second one is the transition probabilities for all possible i's and j's. The transition probability from one state I to state j. And the third one is the initial probability distribution, namely the probabilities with which we start the Markov chain from any state. And we denote this as pi I, so I is state I, yeah, 0. So this looks like a function pi I 0 because 0 at that in this notation is simply the time at time 0. So the distribution, the probability of starting at state I at time 0 is equal to the probability that x0 is equal to I. Now, point 2 and 3 can be perfectly well encoded by a transition probability matrix and an initial probability vector. A transition probability matrix is simply a matrix that contains all of this probability, transition probability, or probability of transitioning from state I to state j. That means that Pij in this matrix is simply this one, namely the probability that currently we are at state I and the next state will be state j. Yeah. So for example, P32 will be the probability of residing right now at state D. If the DTMC is at state 3, then the next state it will be transitioning to state 2. This is the transition probability matrix. Of course, some of these elements of this transition probability matrix can be 0, but they cannot be negative. The second one is the initial probability factor. So this initial probability distribution is encoded right now in a factor. So we call this a factor pi 0. Why? Why do we have 0? The 0 basically denotes the distribution at time 0, how it looks like at time 0, which is equal to pi 1 0, pi 2 0, pi 3 0, and so forth until pi m. So starting from state 1 until state m. This is one way for us to describe it. Yeah, and this is a very convenient way because it it shows us in terms of a matrix. But there is actually another more intuitive way to specify a DTMC, namely by using the transition probability graph as shown here. Now in this case, a state in the DTMC will be represented by a node or a vertex in the graph. Yeah, so will be represented by a vertex, and then there will be edges between these vertices, where an edge basically represent a transition. Yeah, in the discrete time Markov chain. And now these edges will be decorated by the probability. Yeah, by the probability of those transitions. For example, we look here in this figure that there are 4 states in fourth, namely represented by vertices 1, 2, 3, and 4. And we see also that there are many transitions represented by the edges, and above this transition or close to this transition or edges, there is a decoration that tells us basically the probability. For example, this simply means that there are 2 outgoing transitions from state 2, namely one of them with probability 1 minus r, and the other one happens with probability r. And also actually we can also here represent the initial probability distribution, namely by an arrow to the state. Yeah. Now in this example, it happens that the initial probability distribution, the probability distribution is equal to 1 to state 1 and 0 to other states. So that means that we don't have to draw them for other states, for states 2, 3, and 4. Notice that actually we don't draw all of the transitions. All transitions that occur with probability 0 are simply neglected. Yeah, that means that this is actually not exactly the same as the transition probability matrix, because in the transition probability matrix, transition that happens with probability 0 are still there. We can still see it, but right now we just ignore the transition or the edges that happens with probability 0. Now, if we look back again to this discrete time Markov chain, we see that it represents something about failure behavior. So, originally, let's say that a system basically is working, namely residing at state 1, and sometime afterward it may be broken. Look at this, the forming transition B here with probability B, yeah, at time step, or it may be skip working with probability 1 minus B. Now once it is broken, it can be repaired with probability R, yeah, and if you don't repair it, there can be another problem, and we can also repair it. But if you don't repair it 3 times, then we have 2 times, we then we replace it, for example, and then we transition with probability 1 from state 4 to state 1. This is what we call transition probability graph. Now, of course, it is not really difficult for us to represent this again back to the transition probability matrix and the initial probability factor. Namely, this is basically the transition probability matrix. So this represents state 1, state 2, state 3, and state 4, and so forth. So that means that there is a probability of 1 minus b to transition from state 1 to state 1. This is P1, 1, and so forth. And then look to this initial probability factor. So we start with probability 1 at state 1. Okay. Now, there are many questions that we are going to ask once we have a discrete time Markov chain. One of the most important questions is about the probability of being at one particular state after some times. What is actually the probability of being in state? So we start executing this or running this discrete time Markov chain, and we just keep it like that, and then we observe its behavior, and we are interested in usually two things. The first thing is that what is the probability that the CTMC will end up at one particular state after some time? And then the second one is what is the probability of end up in another in one particular state after a lot of time is a long behavior, after it enters some sort of equilibrium and so forth. Now, both of these cases rely on our knowledge about the probability of a path. Yeah, what is a path? A path is just a sequence of state. So the definition of path in this case is similar to the definition of path in graph. Yeah, so we have some path. Let's say some path basically traces the states that we traverse during the execution of this DTMC, of this discrete time Markov chain, and we look at it. For example, here, given a path, our path in this example here passes through state 1 first, and then going to state 2, state 3, going back again to state 1, to state 2, and state 3, and so forth. So we can denote this, namely x0, namely the state we are residing at time 0 is state 1, x1 is 2, x2 is 3, x3 is 1, x4 is 2, and x5 is 3. Now, if we are asking a probability of a path, this simply means that what is the probability of this particular path? The probability is equal to x is equal to the probability of xn is x5 is equal to 3, namely at time 5 we are at state 3, and x4 is equal to 2, and x3 is equal to 1, and x2 is equal to 3, and x1 is equal to 2, and x0 is equal to 1. So this simply means that we are ending them, because that's basically the path or the steps that we are taking. We start from 1, going to 2, going to 3, and so forth. Okay, now, what can we say more about this? Well, actually, if we look at this, we can right away use the conditional probability. Conditional probability says that the probability of A given B is equal to the probability of A and B divided by the probability of B. Or another way of saying this is the probability of A and B is equal to the probability of A given B multiplied by the probability of B. So if we look at this as an ending of them, then we can basically partition them. We can say that this is the same as the probability that x5 is equal to 3 given that x4 is equal to 2, x3 is equal to 1, and so forth, multiplied by the probability that x4 is equal to 2 and x3 is equal to 1 and so forth. So you see this one. But then if you look at this, this is easy to see that we can do this repeatedly for this case right now. Yeah. So we can expand this again. We see that the probability of x is equal to 2 and x3 is equal to 1 and x2 is equal to 3 and x1 is equal to 2 and x0 is equal to 1 is equal to the probability of x4 is equal to 2, given that x3 is equal to 1, x2 is equal to 3 and so forth. And we can do this repeatedly, yeah, again and again. So we can basically apply this conditional probability, the definition of the conditional probability, to this probability of path. Yeah, and we are ending up in this expression here. So if we do this repeatedly, we end up in this expression. So the probability of that path then is equal to the probability of x5 is equal to 3, given that x4 is equal to 2 and so forth, multiplied by the probability of x4 is equal to 2, given that x3 is equal to 1 and x2 is equal to 3 and so forth and so forth. And what can we do right now? Well, because this is a Markov chain, it must satisfy the Markov property, the memory list property. The memory list property says that these facts here are irrelevant. So that means that we can actually just remove them. Yeah, these expressions here are irrelevant. This also is irrelevant, and this one is irrelevant. So therefore we can simplify this simply as that. The probability of x5 is equal to 3, given that x4 is equal to 2, multiplied by the probability x4 is equal to 2, given that x3 is equal to 1, multiplied by the probability of x3 is equal to 1, given that x2 is equal to 3, and so forth. But then we also have known how to find this one. This simply means, the probability of starting at 2 and ending up at 3. So we can look at the content. We can look basically at the elements of the probability or of the transition probability matrix. Yeah. So if we continue this one, well, the only thing left is this one, and this is actually the initial probability distribution. Namely, we can find it in the initial probability factor. So this is the same, therefore, as this one is P23, P23 multiplied by P12 multiplied by P31 and so forth until the last one multiplied by the probability that x0 is equal to 1, which is equal to, you can look at the probability, the transition probability matrix is equal to 1 minus r multiplied by b multiplied by r multiplied by 1 minus r multiplied by b. So this is looks like the other way around in the path, yeah, multiplied by pi 1 0. So therefore we can conclude that the probability of a path is the products of all transition probabilities that are passed through or that are traversed in that path. This is the end of our discussion about the discrete time Markov chain.